right than last year. I was walking home and I dropped my planner and I kicked it and slid it off the hall.
Okay, guys. Lesson 36 is critical numbers, and just a little bit about them. Okay, so critical numbers are an important part of calculus and derivatives as we move forward. Excuse me, really derivatives and integrals. So, definition up there. A critical number of a function f is a number, C, in the domain of f, where either the derivative at that point equals 0 or the derivative does not exist. Okay, so critical number. Critical number happens either where the derivative equals 0 or the derivative does not exist. Those are the two instances where you'll have critical numbers. When this happens, again, these are points that we always want to investigate in various problems that you'll see coming up in the future. So right here, these are instances where the derivative of a function do not exist. So, you guys recognize this first graph, yes? What graph is this? Yeah, this is absolute value of x. And when you think about the absolute value of x, the catch here is right here at x equals 0. At that point of that v, that is a sharp point. And right there, you cannot take the derivative where there is a sharp point. Okay, so that is a situation where the derivative does not exist. So I'm going to write right here, no sharp points. Okay, so no sharp points. If there's a sharp point, you can't take the derivative right there. Now, that doesn't mean I can't take the derivative to the left of 0 and to the right of 0. I just can't take the derivative at that sharp point or hard point, whatever you want to call it. Curves, soft curves, those are all good. It's the hard points that are bad. So as we look at example 2, or that second graph, notice again there is another sharp point. Yes? This is a different graph, another sharp point. That is another place where the derivative will not exist. I don't know, you guys probably can't tell it. This would be the graph, or it's designed to be the graph of x to the 2/3. If you remember, x to the 1/3 is, we talked about this on the review worksheet, where x to the 1/3 is the sideways x cubed graph, and x to the 2/3 is where that lower piece would flip up, and it gives it that hard point right there. So again, there's a hard point. We can't take the derivative, does not exist. And third example, okay? This is designed to be the graph y equals x to the 1/3, I believe. Notice, are there any sharp points here or hard points here? No. But what we do have is we have a section where if we were to draw a tangent line, we would have to draw a vertical tangent line. And so right there, that is a situation where, again, the derivative does not exist. It's fine on the curves and stuff. It's just right there at that part that flattens out at x equals 0. Okay, so those are some examples of where they do not exist. Key point here, if f, so if a function has a local or relative maximum or minimum at a point C, then C is what we call a critical number of f. And I will explain that here as we look at the graph, but the point being stated is if there's a max or a min, basically, then that is a critical number. And look at the situation here. As we look, let me slide this. Okay. Here's a graph that shows all the following places are local or relative max or minimum values of the function drawn. So this first one, what do you notice about where that point is? It is a sharp point, right? So if it's a sharp point, what did we just talk about the derivative? It would not exist. What about at point B? Is that a sharp point? No, it's a what? It's a minimum. And what happens at a minimum to the derivative? It's 0. Because remember, on a minimum or a maximum, the tangent line you draw would be horizontal. And what kind of slope does a horizontal line have? 0. So at point B, there's an example where the derivative equals 0 because it's a horizontal tangent line which has a slope of 0. At point C, what do we know about the derivative there? Does not exist because, again, it's a hard point. What about at point D? It'd be 0. Because at point D, there's a minimum. It's just a regular curve, but that means the horizontal tangent line is a slope of 0. And at point E, derivative would be 0 because, again, this time you have a max, but it's a horizontal tangent line. Okay, so there is your visual of, okay, if derivative equals 0 or does not exist, mins and maxes are great places for this to happen. Okay, and as I said, critical numbers can be used for a lot of things moving forward in calculus. And so that's why it's such an important thing that we learn how to find critical numbers. So let's look at example 1. The directions ask us to find the critical numbers of the function f of x equals x to the cube, x to the third, plus 9 halves x squared, plus 6x, plus 5. Also find where the relative max and min values occur. Okay, so let's start with the idea of finding the critical numbers. How are we going to find critical numbers?
Find mins and maxes.
How are we going to find mins and maxes?
Graph it.
Yeah, we're not going to graph it. This is the how do we find the mins and maxes without a graphing calculator. That's what this is. Okay, so this would be a non-calculator type problem on an AP Calculus test. Critical numbers. What do we say about critical numbers? Where do they occur? Where either you can't see up where I'm pointing, up at the top of the page. Critical numbers occur where either the derivative equals 0 or does not exist. Okay, so take the derivative, not plug in 0, but so set it equal to 0. Okay, so when it's the derivative equals 0 is when a critical number occurs, is when the derivative equals 0. So we need to find the derivative and set it equal to 0. So let me write down my original equation, f of x equals x to the third plus 9 halves x squared plus 6x plus 5. F prime of x, derivative skills, let's go. It's derivative of x cubed, 3x squared, plus derivative of 9 halves x squared, multiply by 2, cancel out, so 9x, plus derivative of 6x, 6, plus the derivative of 5? 0. So what do we do with this derivative? Set it equal to 0. So 3x squared plus 9x plus 6 equal to 0. And this is where algebra skills. So much of calculus is algebra skills. Okay. I would definitely either factor out the 3 or, in all honesty, because this is an equation where both sides have something, we could actually just divide the 3 away. You could factor it just the same, but because I can divide, because there are 2 sides to this equation, I can divide both sides by 3. So if I divide everything by 3, this becomes x squared plus 3x plus 2 equals 0 still. Good news? We can factor this, yes? As I said, it's all algebra at this point, at this exact moment. X squared breaks into x and x. What numbers? Okay, plus 2 and plus 1 because we need them to multiply to be 2 and add to be 3. What do we do to actually solve this? Yeah. Officially, it's set each part equal to 0. X plus 2 equals 0. Or x plus 1 equals 0. What does x work out to be? Negative 2 and negative 1. What are these?
Zeros.
They're zeros. They're also critical numbers. They are places that make my derivative equal 0. So right there, this answers the first part of the question, which said to find your critical numbers. Okay? So when you're asked to find critical numbers in homework, take the derivative, set it equal to 0. And this will be critical numbers. Now, if you recall, it said if f has a local or relative max or min, then there is also a critical number at that point. This wants to know where the relative max and min values occur. Thoughts? What do we know is happening at negative 2 and negative 1 if they are critical numbers? Okay, sharp point or min or maxes. In this case, we're going to be talking min or maxes. Okay. Do you know if there's a min or a max at negative 2? Do you know if it's a min or a max at negative 1? We don't necessarily know that, do we? Now, go back to the original problem. My original problem was f of x equals x to the third. I know we don't know based on the rest of this, but what kind of overall graph is this? Before we took the derivative, this was a x to the third, so it's a cubic, right? What are options for how this cubic graph could look? Okay, 2 mins and maxes. Can you visualize cubic options in your head for what that graph looks like? Was it in this class we talked about the other day? We drew some options?
Yeah.
Actually, that's the video I recorded, wasn't it? So if you all watched it, I showed some there. But first of all, it's positive x cubed. So that means we have to start low and end high, yes? So basic cubic could look like that. However, Are there any critical numbers here? No. Okay, and I know just because it's positive x cubed, in behavior is down and up, and it has to start low and end high. The other option is there can be up to 2 mins and maxes. Can you visualize what that will look like? If it keeps that same basic shape, but has a min, a max, and an inflection, or always an inflection point in there. Which one does our graph look like here? Yeah, our graph has to look like this one because we have 2 places where the slope equals 0. So our slope equals 0 twice because we have 2 critical values. Since we have 2 critical values, our graph has to look like that. Now, think about this. If we're going left to right, at -2 and at -1, which one's the min, which one's the max? I agree. Do you guys see why he said this? As we go left to right, which x value comes first? X value of -2 comes first. Max comes before the min in this case, right? So the max is going to be at -2. The min is going to be at -1. Now, the actual relative maximum and minimum values is the y value. So how am I going to find the y values of how high these max and mins are? Okay, and the key point I want to point out, he said plug -2 and -1 in to the original, not your derivative. When you're trying to find your max and min, you're going to plug them into the original. So if we continue to treat this as a no calculator problem, plug in -2. -2 to the third plus 9/2 times -2 squared plus 6 times -2 plus 5. Let's see, -2 to the third is -8. -2 squared is going to be 4. 9/2 times 4. Well, 2 and 4 can cross cancel. Becomes 1 and 2. 9 times 2 makes this 18. Positive 18. And then we'd have a -12 plus 5. Could you guys do all of that without calculators? So -8 plus 18 is 10. -12 is -2. Plus 5 is 3. So what's my ordered pair here? -2, 3. And is this a max or a min? It's a max. Because it's a cubic, and as we move left to right, our max comes first. So if you're asked, where does the max happen? The max happens at -2. What is the maximum value? The maximum value is 3. And we can do this other one also, right? What was my other one? -1. -1 to the third plus 9/2 times -1 squared plus 6 times -1 plus 5. Notice I'm using the original equation again. Let's see. -1 to the third is -1. -1 squared, positive 1 times 9/2 plus 9/2. 6 times -1, so -6 plus 5. I personally would do all the whole numbers first and then worry about the fraction. -1 and -6 is -7, plus 5 is -2. What do you know about 9/2? My brain says 4.5. So if I've got 4.5 minus 2, I'm at 2.5. And you can say 2.5 or you can say 5/2. It just depends on your feelings. And so this ordered pair, -1, comma 2.5, and it is a minimum. The minimum occurs at x equals -1, and the minimum value is 2.5, 2.5, 5/2. Whatever makes you happy there. Okay. Get a little bit of the idea there. So we're going to retry this with another problem now on the back. Okay, example 2. Find the critical numbers of the function f of x equals 1/4 x to the 4th minus 1/3 x cubed minus x squared plus 5, and indicate where the relative maximum / minimum values occur. Okay, what am I starting off doing?
Yeah, but
There's still like
okay.
True, we won't have middle school going to lunch, but we will have high school coming back from lunch.
Yeah.
I don't think there's any high school in the middle lunch.
I don't want to go to B. I know Wyatt used to have B lunch because he ate for food.
Yeah, but that's why he sits in the library now, so he doesn't have to go to B lunch, I think. So, okay. So, I think you guys probably told me what we were going to do here. Let me write down my original equation. F of x equals 1/4 x to the 4th minus 1/3 x to the 3rd minus x squared plus 5. So what did you guys start off doing? Take the derivative. Critical numbers. Anytime you hear those wordings, critical numbers, derivative. So 1/4 x to the 4th, x to the 3rd, minus derivative of 1/3 x to the 3rd, x to the 2nd, minus derivative of x squared, 2x, plus derivative of 5, 0. What do we do with this derivative? Set it equal to 0. Again, every time critical numbers, think derivative equal to 0. Okay, let's change that wording. Last time, I was willing to factor or divide by 3 because 3 was a constant. This time, I will not divide by x. Because if you divide by x, you have just divided away one of your critical numbers. Okay, that's my point there. So what do I have to do here since I won't let you divide by x? You have to factor out a GCF of x. Okay, so if we factor out an x, it becomes x times x squared minus x minus 2. What can I do now? Yeah. Can we factor our trinomial into 2 binomials? X squared becomes x and x. What numbers you got for me? -2, +1. Now what? Hold that thought for a moment. Okay, officially set equal to 0. What about all of my setting equal to 0? Okay, x equals 0. Whoops. X plus 1 equals 0. X minus 2 equals 0. So the values I'm going to get out of these are 0, negative 1, and 2. What are these values? Okay. Critical numbers. Now, yes, the idea is once you have your critical numbers, they're asking us to find where our relative max and min values occur, yes? Now, the big thing I want to know is what's maxes and what's mins? So what kind of graph are we talking about here? What? Okay. It's an x to the fourth. It's a quartic. I showed you quartic on the lesson I recorded last week, right? Okay. A basic quartic looks like a flattened parabola. However, is that what I have here? No. So we need to have one of these W options. Whether it's a W option that's somewhat equal. You say a parabola with a parabola? And the key is the parabola with the parabola lopsided or is it equal? Okay. Yeah. The key is here, our critical numbers, we have 3 critical numbers. So our slope equals 0 3 times. Which is why we know it's not the first option, it's one of the other 2. Now, what does that mean is happening? We're going to have what? A min, max, min. No matter which one it is, it's a min, max, min. Min, max, min. So now, as we think about min, max, min, think about your critical numbers in order. And if we think about them in order, what's the first one? Negative 1. So f of negative 1 is going to have to be a min. F of 0 is going to have to be the max. And f of 2 is going to have to be the min. Now, how much time do we want to spend on this problem? Because based on what I have written down, the math is not necessarily pretty. Okay? Between your brain and the calculator. We can do this though, right? If you don't mind, I was just going to write down what they are. I just kind of have written in here, plug them in. Yeah. I don't feel like that's not what you guys need me for, right? That's just, So when I plug in f of negative 1, I have written down 55/12. Which means there is a min at the ordered pair, negative 1, comma, 55/12, which you could say 55/12. I also wrote in my notes that it is 4 and 7/12. Guess if you want to do some math, fine. Plug in 0 real quick. 5. Plug in 0, you get 5. This ordered pair is 0, 5, and it is a max. Plug in 2, and it's 7/3. So 2, 7/3, or 2, 2 and 2/3. Okay. Could you check this on the calculator? Yeah. You can graph this on the calculator. You can check your mins and maxes, and they should match up. I just didn't want to spend all of our time just plugging all the numbers in. Okay, we've got one more example. as example 36b. A note about critical numbers. Not every critical number produces a local maximum or minimum. General rule of thumb is a critical number will produce a local maximum or minimum. However, there are exceptions. For example, let f of x equal x to the third. Find the critical values and check to see if it is a max or a min. Okay, well, let's do this real quick. Well, okay, we know what the graph of f of x equals x cubed is, don't we? What's the graph of f of x equals x cubed? Curvy-ish? It's that, right? Are there any mins or maxes on that? No. Let's see where there's supposed to be a min or a max. So, if f of x equals x cubed, what do we need to find? Derivative. So, f prime of x, what's the derivative? 3x squared. What do I do with that derivative now? Set it equal to 0. So 3x squared equals 0. What do you do? Divide by 3. So then we have x squared equals 0. Square root both sides. And x equals 0. So what is this x equals 0 officially? This is a critical number, though. Because we took the derivative, set it equal to 0, this is a critical number. And where is x equals 0 on that x cubed graph? That's in that middle right there. Okay? So in this case, it's not a min, it's not a max. Do you remember what I called that? It's an inflection point. Okay? So it's not a min or a max. If you want to put a label on it, it is an inflection point. Okay? You'll notice down at the bottom it says, these are locations where the derivative simply failed to exist. And what happened in its place is an inflection point, which we'll talk more about inflection points as we go along.
On the other graph, where we had it, and we had like the 2 mins or maxes. Yeah, that's right on the front side. So the reason why we only had 2 values is because there was, you have to count for the inflection point.
Well, you can only have, if it's a power of x to the third, so degree 3, the most mins or maxes you'll ever have is 1 less than that.
Exactly, because you have to count for the inflection point. So it takes up 1 spot.
No, not necessarily. I mean, critical numbers, the most you'll ever, like mins and maxes, the most critical numbers you'll ever have is 1 less than the value of the highest exponent. So it's not really that it takes up a spot, because we still had 2 on that front page.
Well, it just takes up, it's guaranteed to have a spot. So you can only have up to 2 because it already took the first spot of the 3.
But if you're talking about the first one, it was a cubic, which is power 3.
Yeah.
And at most, you can only have 1 less than that power, so 2. It's not that it's taking up a spot, because not all problems are going to have a critical point, or an inflection point. I don't know if that's answering the question or not, but
Yeah, it does.
okay.
So only odd graphs have inflection point.
No. I disagree. So his statement was only odd graphs have inflection points. I'm going to go to my cortex here. Because an inflection point, and we'll learn more about inflection points yet. I don't think we've done, this is the first time I mentioned inflection points last week. Okay, so we have a lot to learn about inflection points. But inflection points are where your graph changes from concave up to concave down. But we haven't talked about concavity yet, have we? So, I mean, concave up is where something like is fold up. concave down is something like that. An inflection point is where it changes from that. So like if I look at this one real quick, sorry, the inflection point is right there in the middle where right here it's kind of curved downward. Right here it's curved upward. Okay, so it's changing that concavity, which again, not something we've talked about. No! I'm trying to show you, of course, trying to show you something on the quartic, that there are inflection points there.
That one they should have colored the background before they typed. Then they had all the closed characters.
Okay, here's what I'm trying to show you. So quartic, as we look at this quartic here, and I don't know if I can really even midway of where right here it's curved up, and then over here it's curved down. So there'd be like an inflection point there, and an inflection point there. What? Sorry. That's not expressed to you, that is technology. That's just me growling at technology today. It's the way the week's going. Okay, so what I was pointing at, you can see right here where I was kind of pointing, but like right here is an example of an inflection point. Because right here it's all curved up, right? And then somewhere here in the middle it changes and now it's curved down. And so there'd be like an inflection point there and an inflection point there. Okay, so inflection points just happen whenever the concavity changes. They can happen with an odd power or a even power. Okay. He's trying to get farther here, aren't you? I do need to end the recording before I go any farther, probably.